last two modules we were discussing optical transmitters, and we looked at three kinds of modulators. One was the phase modulator, which you can use to modulate the phase of the light wave emitted by the laser, and this is used in phase modulated optical systems. The second modulator that we talked about was in construction slightly complicated compared to the phase modulator. This was called as the Mach-Zehnder modulator, which worked on the principle of interferometer. This we have seen that the relationship between electric field input and electric field output of this particular modulator is a nonlinear function because of the presence of a cosine transfer function. Right. We then combined phase modulator as well as the Mach-Zehnder modulator in order to form an even more complicated structure which can be used to modulate both amplitude as well as phase, and that is actually equivalent to a conventional IQ transmitter that you find in electrical communication systems. This modulator was called as IQ modulator. We will have more to say about IQ modulator later, but let us look at one additional use of Mach-Zehnder modulator today in this module, starting with intensity modulation and then covering up how can we generate optical pulses using Mach-Zehnder modulator. Okay. So, we have already seen how Mach-Zehnder modulator can be used to modulate the amplitude of the incoming light field. There we saw that you have to operate the Mach-Zehnder modulator at its minimum transmission point, and at that point the electric field at the output can be approximately linearized as a function of the input electric field. So, that is, there is a approximate linear relationship between output and the input when the Mach-Zehnder modulator is operated at its transmission points. Assuming that the signals that you are giving, the modulating signals that you were providing to the modulator were very small, then one can see that output and input were related in a linear fashion. The drawback of that one was that when you are operating at the minimum transmission point, then you have to apply a certain voltage to get a non-zero power. So, although you obtained a linear linear relationship between output and input, which could be useful for double sideband suppressed carrier type of modulations, what we saw there was that the output power would be very small because the Mach-Zehnder is biased at its minimum transmission point. Now, in intensity modulation, we are typically not concerned with what happens to the amplitude of the signal. What we really want is that when I have some information signal, then I need to look at the power, and this power, if it varies linearly with the modulation signal, that is all right with me. The reason why it is okay is because if I put a photodetector in order to detect the signal will detect the optical power. So, if I can modulate the optical power itself, then all the variations that I am seeing in the optical power will be directly transferred to the electrical domain in the form of the photocurrent, which can then be used in order to extract the information signal. The disadvantage here is that you have to operate the Mach-Zehnder modulator not at its minimum transmission point or at its maximum transmission point, but at the center, where it means that when you do not have any variation coming in or you do not have any message signal coming in, then the modulator will expend some power, okay, because it would provide, because you are operating it at the bias in the halfway between the minimum and the maximum transmission points, it will produce some non-zero power. However, that is quite interesting to look at how one can modulate the optical power. In order to do that one, let us recall first the relationship between electric field at the output of the Mach-Zehnder modulator, which we will denote it as E out. It was function of time. This is given by the input electric field coming from the laser times the transfer function. Please remember that this transfer function is not the same as the transfer function concept that is used in signals courses. In there, the transfer function actually refers to the Fourier transform of the output variable to the Fourier transform of the input variable. However, we are using transfer function in a slightly general sense. What we are saying is this is the relationship between output electric field and the input electric field. This relationship is in the time domain. It is kind of how the input is transformed or transferred onto the output side. That is what we mean when we say transfer function in this context. Please keep this difference in mind. Now, coming back to the electric field relationships, the output electric field is related to the input electric field in this particular nonlinear manner, as we have seen. There is, in the argument of cos, you have cos pi ud of t. Remember, ud of t is the difference signal between u1 and u2 of a dual drive Mach Zehnder modulator. This Mach Zehnder modulator is being driven by u1 and u2, and ud corresponds to the difference between u1 and u2. So, you have cos pi ud of t divided by 2 v pi. This is something that we have seen. We have also seen how the electric field transfer function looks like when you plot the ratio of E out by E in as a function of ud of t. It would be a cosine waveform. Now, as I said, I am interested in the intensity that is coming out of the Mach Zehnder modulator. Intensity is proportional to optical power. In this particular case, we will assume that intensity is actually equal to power. If there is some conversion factor which we will neglect at this point, and in order to obtain the optical power, as I have told you earlier, you simply need to square this particular component. You have to take the absolute value and then square it. So, when you square, what you get is the output power, and I will leave this as an exercise, okay, to show that the output power of the Mach Zehnder modulator will be equal to half plus half cos of ud of t divided by v pi into pi. Now, you might be wondering where this is coming from. Sorry, this has to be multiplied with the input power, or let us actually divide this one by the input power, so that we are looking at the ratio of the output optical power to the input optical power. If you are wondering where this half plus half cos ud of t pi by something is coming up, you just have to remember that I am taking the square of this right hand side quantity. So, I end up getting something like cos square theta, and I know that there is a trigonometric relationship which says that 2 cos square theta must be equal to 1 plus cos 2 theta. So, if I square it, then I know that cos square theta can be expressed as 1 plus cos 2 theta divided by 2. So, that is, this half is coming from this particular relationship, and because the argument doubles up, that 2 in the denominator goes away, and then this is what the equation that you are going to get. Please verify that you are able to derive this particular equation. Okay. Again, what do we do about ud of t? Ud of t is again the signal that you are applying. Let us plot what will happen to this p out of t by p in of t as a function of this one. When you plot it, you are going to see that when ud of t is equal to 0, cos of 0 will be equal to 1. So, you get half plus half, which is maximum. So, I am actually plotting this particular quantity on the y axis as a function of the applied signal ud of t. Okay. So, when you look at this way, at cos equal to 0, this would be half plus half. So, it would have a maximum value of 1 at ud of t is equal to 0. Now, let us make ud of t is equal to v pi. When this is equal to v pi in the numerator cancels with the v pi in the denominator in the cosine function, in the argument of the cosine function. So, I end up getting half plus half cos pi, but I already know that cos pi is equal to minus 1. So, I basically get a 0 as the ratio, right, at the output would be essentially be 0. This will happen at v pi. Interesting thing would be to look at what happens when ud of t is equal to v pi by 2. So, this is the case when this is v pi. So, when ud of t is equal to v pi by 2, okay, then you see that the argument of the cosine function becomes cos of v pi by 2 v pi, there is also a pi. V pi cancels, right, v pi cancels here, and then you get cos of pi by 2. When cos of pi by 2 is there, this output power, this quantity, the ratio that we are plotting will be equal to half, correct. So, at v pi by 2, this power would have dropped, or this ratio would have dropped to 0.5 or half, and here you actually have a cosine kind of a relationship, which, or cosine square relationship, which would go in this particular manner. It would be a periodic function with a fundamental period of minus v pi to plus v pi. So, I hope that this transfer function is all right. Now, as I said, this v pi by 2 is something that is getting interesting, because you have in this particular case a relationship where if I take the Mach Zehnder modulator and bias it at this point, and then in addition to this I apply a certain m of t, then I will be going over this particular transfer function. As my m of t changes here, the corresponding changes will be on the transfer function, and it would be essentially oscillating around this V pi by 2. So, there is almost a linear relationship which one can have, provided of course that this m of t is very small in relation to V pi by 2, that is the peak value of m of t must be absolutely small compared to V pi by 2, so that this linear relationship or actually the nonlinear relationship can be thought of as approximately the linear relationship. Let us do that mathematically and check what we get. So, let us assume that the difference signal u d of t which I am applying to the Mach Zehnder modulator is given by a DC value which is V pi by 2 plus some constant k, okay, do not worry what that constant is, times m of t. M of t is this small signal that I am applying. If you have studied transistors or diodes, you would remember that you have to bias a transistor at a particular operating point, correct. This operating point is sometimes called as the Q point, and then you have to apply the AC signal which is very small in relation to the DC signal. So, if you look at a typical transistor circuit, your operating point will be somewhere in the middle of the operating region of the output characteristic of the transistor, but the AC signals will be in the order of a few millivolts. So, that AC signal is essentially this m of t which we are applying. So, as the voltage changes on the input side, u d of t starts off at say V pi by 2, then increases and until it reaches the peak value of m of t, and then it comes back to the minus m of t value. The corresponding changes that would happen will be happening on this transfer function. So, this is the range of input and output that you are operating, and over this range you can consider the Mach Zehnder modulator to be a linear function in the power, that is output power is linearly related to the input power. Okay. So, with that if I substitute math, so of course we have just said this in graphical way, let us quickly do the math in order to see what we are talking about is reasonably okay. So, you have the difference signal u d of t which is equal to V pi by 2 plus some constant k into m of t. Now, I substitute this into the expression here, let me call this as equation 1. So, let me substitute this one into equation 1 and then simplify to find what I get, right. So, the ratio here will be P out by P in of t, right. This is equal to, this is the left hand side of equation 1, this would be equal to half plus half cos of V pi by 2 plus k into m of t into pi divided by V pi. I can expand the argument in the cosine one, let me just take that part here and say cos of V pi by 2 V pi is here, plus there is a pi k by V pi m of t. Okay. Again this k being a small number, this pi k by V pi itself is very small compared to this pi V pi by 2 pi. V pi in the numerator cancels with the V pi in the denominator, and this pi k by V pi can be considered as another constant. Let us call this constant as some k prime. There is no significance to k and k prime in the sense that they are just constants which have to be considered in order to just to denote this number k, pi k by V pi, I am denoting it by k prime. Okay. All right. So, with this one I can expand here, right. So, what I get here is cos pi by 2 plus some constant k prime times m of t. Now, I know that cos of pi by 2 plus theta can be written as cos pi by 2 cos theta minus sin pi by 2 sin theta, and I know that cos pi by 2 is a 0. So, that term goes away, and I know sin pi by 2 is equal to 1. So, this cos of pi by 2 plus theta is actually equal to minus sin theta. So, I can write down this in this way and say the ratio P out of t, or rather P out of t itself is equal to P in of t, right. This is the input power from the laser, times half minus half sin, what is theta? Theta is actually k prime m of t. Of course, we also have another relationship which says that when sin theta is very small, when theta is very small, then sin theta can be approximated as, sin theta is approximately theta for theta very small, right. So, compared to this one, if theta is very small, then sin theta will be approximately theta. So, theta small is probably a better way to write this one. So, let me just write it like that. For small values of theta, sin theta can be approximated as theta. So, I can remove this sign from here, and I also know that the input power is not varying because I have assumed a ideal laser. Ideal laser does not fluctuate in its amplitude, okay, and its phase is immaterial since we are operating this in the continuous wave, and this laser has a peak power of Ps or the continuous wave power of Ps. So, I am going to write this as half Ps, and then I have 1 minus k prime m of t. As I said, do not be alarmed by this minus sign. You have to remember that this k prime is a very small quantity. So, because this is small, we have been able to make these approximations. Okay. Because k prime is a small quantity, all you are seeing is that if you were to plot p out of t as a function of time and assume that m of t is equal to 0, then the power that you are getting at the output would be half Ps and it would be a constant. Over and above, if this m of t would say for example be a sinusoidal signal, then over and above is what your power would be fluctuating. So, this half Ps is the average power, assuming that m of t is something that would average out to 0. So, this half Ps is the power. You can think of this as the average power or the power that you would obtain when m of t is equal to 0, and when you apply m of t to be a sinusoidal signal of something, then the fluctuations will be having a magnitude of k prime, in the sense that the peak value will be k prime and this entire thing would be, the peak to peak variation will be 2 k prime. Okay. So, you can see that there is a linear relationship if you forget, if you are looking at the change in the output power, okay, rather than looking at the output power itself. If you are looking at the change in the output power, this change in the output power can be obtained by removing this DC component half Ps, okay, and then what you have is minus half k prime m of t, right. So, I can see here that I have removed the DC part, but the change in the optical power can be negative. Of course, this implies that this does not imply that the power itself is going negative, but please remember this is only the change in the optical power. So, what we have obtained here is that we have obtained a, oh sorry, there is a Ps by 2 also, I am sorry I forgot to put that one. So, this change in the optical power is this fellow where k prime is a very small number. So, this would essentially be the output, right. So, you have now seen that if you are looking at the change in the optical power, that can be a linear function of the applied m of t, right. So, there is a linear relationship. This can be used for intensity modulation of analog signal. So, if m of t is an analog signal, then you can actually use that to use the Mach Center modulator to obtain the output power, which is varying as in accordance with the input message signal m of t. Having seen this intensity modulation, let us move on to a different application of MZM. Okay. In optical communication systems, it is typical of the systems that we transmit information. When we modulate the information onto the light signals, we also want the light signal to be pulsed. So, we send out optical pulses carrying information. These optical pulses can carry information both in their amplitude, phase, or in general the quadrature amplitude modulation. However, optical pulse shaping simply implies that I am able to generate optical pulses and then modulate these optical pulses using any of the modulators that we have discussed. Now, having optical pulses is an advantage because it will let us know where the particular symbol boundary is ending. So, if I have to have a clock and I am not able to send a clock from the transmitter to the receiver on a different channel or something, then I have to extract clock from the optical pulses, extract clock from whatever I am getting. So, when I have optical signals in the pulsed form or I am getting optical pulses, then it becomes very easy for me to extract the clock in order to synchronize both transmitter and receiver. So, for this reason we use optical pulses. We also change the shape of the optical pulses in order to combat the fiber induced impairments. As you will see later, fiber introduces impairments such as chromatic dispersion and nonlinear effects. So, in order to overcome these, we also pulse shape, not just in any arbitrary pulse shape, we choose specifically that pulse shape which can combat dispersion as well as nonlinear effects. So, we do that, and it is therefore necessary that if we have a continuous wave laser, as you would get in most lasers when you purchase them in the market, then you need to be able to generate pulses out of this continuous wave laser, right. So, in order to do that one can either have a pulsed laser by itself, but that would be a different approach. But if I have a continuous wave laser, then I can use the Mach Zehnder modulator to generate optical pulses. Okay. In order to see that one, let us go back to the power transfer function of the Mach Zehnder modulator. So, I have as a function of the difference signal ud of t. Okay. The power transfer function is of course something that we have seen here. So, this is the power transfer function. So, let me operate it like this. It is periodic, as I said. These values are V pi here, this is 0, this is minus V pi. So far let us just use this one, that is this region we will use because that is more than enough for us. Now this is my ud of t. Suppose I take ud of t and then bias it at halfway point, in the sense that I take ud of t and then have its average value given by V pi by 2, and then I also have it as a sinusoidal signal. Okay. Sorry, this should have come and met the horizontal axis. So, I have this as a sinusoidal signal whose peak value is also V pi by 2. So, that the peak value of ud of t that I am getting will be equal to V pi, and then its minimum value will be equal to 0. So, if this is something that I am looking at, this is as a function of time, this is the ud of t. So, if this ud of t is presented to the Mach Zehnder modulator, what would be the output of the modulator? Well, if you remember again your BJT or diodes, you would have come across a concept called as a load line. So, you have a diode, right, which you would be biasing at a certain operating point, and then you vary the input, okay, whatever input current or the voltage, and the corresponding variations can be obtained by this particular load line concept. So, you just have to look at what would happen to the voltage here and then find the corresponding output voltage and then plot it. So, this would be the variation. Of course, I am not really drawing them nicely, but this is essentially what you are going to do, right. This is what you would have done in your earlier circuits courses. So, a same idea we will use. What we will do is we will plot this ud of t as a function of time. Okay. So, these are two slightly different graphs. So, these are two different graphs, please keep them in mind. However, I am aligning these graphs so that I am able to capture what I was telling to you about this load line concept. So, because ud of t is equal to V pi by 2, the average value is V pi by 2 at this particular time. Let us also draw first ud of t, that I can draw it in this manner, and as I said, the maximum value will be V pi, the minimum value will be 0. So, my signal will be between these values, right. I am drawing only one period of this wave, that is enough for me to illustrate the concept. You can extend this to any periods that you want. Okay. So, this is time t equal to 0, and let us say this has a total period of capital T. Okay. So, this part where it goes to 0 is about t by 2. Okay. So, this is about t by 2. Okay. This is ud of t, of course. At time t equal to 0, the value of ud of t is equal to V pi by 2. What would be the corresponding output? The output value will be at V pi by 2, in this case it would be half, we have just seen that one, right. So, this would be half. The scales may not match correctly, so please keep that in mind. The scales are probably not matching, but I hope that you get the idea of how to draw these outputs. That is what I am more interested in. So, let me also erase this portion, erase this slightly. Okay. Here what I do is I put out the output waveform. So, let us call this as P out, and I am plotting P out as a function of time over this particular graph. Okay. So, I have aligned them so that I can better capture whatever that is happening at the input to the output. I can actually obtain this kind of a nice plot. So, at t equal to 0, ud of t is equal to V pi by 2. So, the output would be at half. So, this value will be half. Okay. Then what happens? As ud of t continues to rise here and reaches a maximum value of V pi at t by 4. So, this fellow is at t by 4. The corresponding change that would happen on the Mach Zehnder modulator transfer curve is that this would go down here. As this increases from V pi by 2 to V pi, the corresponding output actually goes down here, correct. That is what you can actually do that by pairing off each point like this. So, pair off these points, and eventually when you pair to the point at V pi, which the modulator is going through at t equal to t by 4, right, the output of the Mach center modulator would have gone down to 0. So, I have to start from this value of half and then come down to 0 at t by 4. Alright. So, I hope that this portion is okay. Now, look at what happens as the modulating signal ud of t or the drive signal ud of t is going down, right. It starts at V pi and then keeps going down, but this movement or this change of signal, right, will be reflected by the transfer function going or rising from 0 to the corresponding half, correct. So, I have to now go back and then get to this portion, which anyway I was there at t equal to 0, but now I am repeating that one at t by 2, because at t by 2 the modulating or the drive signal has come back to V pi by 2. Further, as this signal goes down, right, so here it is going down to 0, the corresponding change that happens on the Mach center modulator will be that corresponding to this one, this is the output. So, it would actually start to go up and then eventually reach to 1, right. So, it would go up and eventually reach to 1. So, let me just write down this one. So, at this point, so it is not, as you can see, the scales are not really looking correctly, for a half I should have gone up. So, let me try do that one. So, the scales correspondingly should have been chosen. So, let us say this is 1. So, it would have gone to this portion, and then once this comes back from 0, right, once it again rises back to V pi by 2 at time t. So, this was happening at 3 t by 4, and then finally when you come down to t, the output voltage would have come back here. Okay. This is how you can use the Mach center modulator to plot the output. Okay. This does not really resemble a pulse, because after it has come here, then it would go down and then it would essentially be a signal that would be rising again. So, it is not really looking like a pulse. So, in order to obtain the pulse, this was easier for me to discuss with you. So, therefore, I used this particular curve, but to obtain pulses we will have to operate this Mach center modulator at a different operating point. So, let us choose first this point, which is the maximum transmission point, and then have a excursion all the way to V pi and minus V pi. So, let us apply that signal. So, now that we have understood how to plot, I will be little quick here. So, I am plotting ud of t here. This would be the transfer function which I am plotting, right. So, this is the transfer function. So, this is at 0, this is V pi, this is at 2 V pi, this is at minus V pi, this is at minus 2 V pi. So, this is the transfer function of the Mach center modulator. This is the ratio P out to P in. Now, I have to put down one other graph which will capture ud of t for me, right, as a function of time. Then I have to also put down one more graph which will capture this ratio P out to P in as a function of time, right. So, I will have to capture this particular thing also. So, let us do that. In this case, I will assume that ud of t is 0 initially and then goes all the way to V pi. Okay. So, it will go to V pi and then go to minus V pi and then come back. Okay. So, it has a peak voltage of V pi. Average value of this fellow is at 0. So, at t by 2 it would be, so this is at t by 2 and this would be at t, where it would have made a complete one time period. Okay. Now, let us plot the corresponding output. Initially, corresponding to this 0 voltage at t equal to 0, the output of the Mach center modulator is at its maximum. As the voltage continues to rise and reaches V pi at t by 2, the output of the Mach center modulator starts to go down and reaches here to 0 at t by 4. So, this is at t by 4, and then from t by 4 the input ud of t starts to drop Okay, so it starts to drop and it goes down to 0 at t equal to t by 2. So similarly, what will happen over here, this will now begin to change from here. So as you come down here is equivalent of going on along this particular direction on the transfer function of the modulator. So it will actually go up and reach your peak at t by 2. So at t by 2 you have now reached a peak. Then what happens, the input starts to go negative, right? It would continue to go negative and reach minus v pi at t equal to 3t by 4. However, that corresponding change on the Mach Zehnder modulator would be that you start dropping in the power from maximum here all the way to 0 when you reach minus v pi. So at 3t by 4 you would have gone down here again. So this would be 3t by 4, and finally we will complete this output and we will be back to where we started at t equal to t, right. So at t equal to t this voltage will be 0, so your power would go back to peak. Now what you can see here is that you have managed to obtain one pulse here, correct. You have managed to obtain one pulse here, okay, which lasts about t by 2 seconds. Why this would be t by 2 seconds? Well, you just do 3t by 4 minus t by 4, what you get is 2t by 4, which is equal to t by 2. So you have now obtained one pulse of duration t by 2, but if you look at this way and then realize that this signal is not just one period, but this is actually a periodic signal, you would immediately realize that there would be one extension this way and there would be an extension along this side as well. So this is your t by, so this is your t actually, the total time period t, and in that time period t you have actually managed to obtain two pulses, right. You have obtained two pulses, one pulse from t by 4 to 3t by 4 and one more pulse. If you remember that this signal ud of t is actually a function of time, so you will have obtained one more pulse. So if this would be minus t by 4. So in the total time period of minus t by 4 to 3t by 4, which would correspond to one time period t, you have obtained two pulses, right. So each lasting t by 2 seconds, you have obtained two output pulses, okay. In other words, if my frequency of the signal ud of t is f0 hertz, right, if this is f0 hertz, the pulses that I obtain will be at a rate of 2 f0, right. So I obtain pulses at double the data rate. So if for example I want to generate pulses for my use for a 10 Gbps modulation, 10 Gbps digital modulation, and I having one pulse carry one bit of information, then I need to generate pulses at one pulse I require at the pulse rate is 10 Gbps, but the signal that I need to apply will only be half of that. So 10 by 2, which is equal to 5 gigahertz, because each half portion of the sine waveform ud of t is giving me. So within one period, if this corresponds to 5 gigahertz, there would be two pulses. Therefore the data rate which I would be obtaining will be double the modulating thing. So the pulse rate will be twice the frequency of the drive signal, analog the sinusoidal signal that you are driving the Mach Zehnder modulator. Now this is not the end of the pulse shaping business. There is one other pulse shape that is also widely used, okay. In order to obtain that pulse shape, we again start from the transfer function. This time let me be even more quick. This is the transfer function as a function of ud of t. I am going to put one more here as a function of time to obtain p out by p in, and then now I consider a signal. This is ud of t, this is in time. I now consider my modulating signal in this fashion. So this is going all the way to, okay, 1 second. So I consider the modulating signal which will go to a peak of v pi or the peak value of v pi, but at 0 or the average value of this one will be at v pi, okay. So the average value here is at 0, I mean the value of the ud of t signal is at 0, and this would be time t by 2, this would be the total time t, okay. Now what would be the corresponding output? Well, initially when you are at V pi. At t equal to 0, the initial amplitude of the ud of t signal is at V pi. So, I put a V pi here. So, the output would be 0 here. As the input increases and reaches to 2 V pi, this value is 2 V pi, the corresponding output would have reached to maximum. Okay. And then once you start dropping, you reach at t equal to t by 2, you would start to drop, and then corresponding output would have gone down to 0. Okay. So, this is t by 2, this is 0, and then you would again see that there is one more pulse that you are going to get at t. Okay. So, if you compare these two waveforms, you will see that the area occupied by these two waveforms are slightly different, although I have not shown it very nicely, but they are actually going to be slightly different, and these two are therefore called as 33% and a 67% waveforms, okay, which simply indicates the percentage area that these pulses carry compared to one period. Okay. So, we will not go further beyond this pulse shaping thing. We will talk about pulse shaping in the electrical context later on, but for the optical pulse shaping we will stop with these two pulse shapes, because these are easy to generate and they are therefore widely used. Okay. Now, I should also point out one additional factor over here, that you can not only get these pulse shapes, you can actually get arbitrary pulse shapes, right, by changing m of t or changing ud of t, and by choosing different biasing points of the Mach center modulator. So, in this example we have biased the Mach center modulator at its minimum transmission point. It is possible for you to bias it at any value. In fact, you can send in any complicated signal and then find what would be the output of the Mach center modulator. Now, you can do all that in simulation by using MATLAB and writing a simple program to generate, to give this as one input and write down the transfer function of the Mach center modulator, the power transfer function of the Mach center modulator, and then find out what kind of a pulse shape that you are going to obtain. You can look for such MATLAB programs in the assignment section, and you will be able to generate various pulse shapes and confirm for yourself that it is indeed what you are obtaining is something that we have obtained intuitively by drawing here. Okay. So, you can pick different operating points and therefore get arbitrary waveforms. So, we will end this module by optical pulse shape. In the next module, we will talk about some fundamental topics that are required in order to better continue the course. Okay. So, these topics will be from signals, systems, and a little bit of communication theory. We will look forward to that in the next module. Thank you.